Hello, everyone. My name is Nader Chmait. I'm at the Faculty of IT at Monash University, PhD student. And today I'll be talking about observation, communication, and intelligence in agent-based systems. Sorry if I go a little bit fast, but due to time constraints, excuse me. So I'll start by describing the problem. Well, the intelligence of multi-agent systems is known to depend on the observation and communication abilities of the agents. We know that, but we don't know which one has a higher influence. It's not clear. And we don't know how do these factors, communication and observation, depend on each other in a multi-agent systems. So what we're trying to do is to actually measure the influence of these two factors on the intelligence of agents and see how they depend on each other. So just a simple graph. So imagine that you have agents here, and what if you increase the communication range or the observation range in the environment? What would happen? How would this reflect on the results? Why are we doing this? Well, first, to the best of our knowledge, we don't know of anyone who actually used intelligence tests to measure such things. And in real-world multi-agent systems, agents have limited sensitivity of the environments, right? So sometimes it's critical to increase their communication and see how we can improve their performance. So this would have a lot of implications because it will allow us to understand the rules of information aggregation between the agents and allow us to predict their usefulness, okay, or the expected performance of these systems under different settings. So we use the word quantify. So we have a lot of problems that are relevant to multi-agent systems, but not every problem is an intelligence test, or not every metric is an intelligence test. So we need to be able to quantify or measure. That's why we will use machine intelligence tests. And we'll try to evaluate groups of agents in different settings. And we will run some controlled experiments where we change the observation and communication abilities of agents. And then we record the results and see what happens. So we'll use the Anytime Universal Intelligence Test, which was developed by Hernandez Orallo and Dowe. And why? Because the test is derived from formal mathematical considerations, and we know that it can be implemented, and it follows the definition of universal intelligence somehow. And we will use the agent environment framework, where we have at each iteration of the test, we have an environment that sends observation to agents, and these agents communicate together, and then they will perform an action. And based on the quality of this action, the environment will send back rewards to these agents. So we'll use the Lambda environment, which is a very simple setting that implements the Anytime Universal Intelligence Test. And just think about it as a grid of cells where you have a group of agents that can move in these cells, so they can take different actions. And we have two special objects, good and evil, and these objects put some positive and negative rewards in the environment. These special objects have a movement pattern, which we can calculate the difficulty or the complexity of the pattern by using an approximation of the Kolmogorov complexity of the movement pattern. And I will not talk a lot about this, the properties of the environment. There are 2 or 3 papers which discuss the properties of the environments, but we have to know that it's important to select the right environments for the test. So we can't just use any environment and then say, these are our results, all right? So we have a set of agents, and we want to test them, and it's, if you go off this boundary, you will start up here, so you can't get stuck. So you can't just get positive rewards for 100 iterations, all right? So if we have a set of agents, we'll just talk about local search. We can, of course, talk about different types of agents, like reinforcement learning, Q-learning, SARSA. So if we have a local search agents, we want them to communicate together. So we implemented 3 different communication techniques, which are pretty much known to everyone. Stigmergy, which is modifying the environment by laying off some rewards in the environment. So they don't directly communicate, they just modify the environment somehow. And broadcasting, which is direct communication. So I tell you, I found this reward in my neighborhood, so I send this information to you. And also, we use imitation. So we introduced a very smart agent called the Oracle agent, which knows the best action to take at one time. And we have these local search agents. We put them together, and we say, all right, imitate this Oracle if you are in the same communication range. So we want to measure observation and communication. It's very hard because we need some kind of unit. So we need to make sure, how can we talk about communication or observation? So we will use an information theoretical approach based on Shannon's entropy to calculate the amount of information there is in an observation and the amount of information there is in a communication between agents. So the first thing to do was to calculate the number of bits that is propagated between the agents as the communication entropy, and then the number of bits that of the description of the observation that the environment sends to the agents, right? So now we have both observation and communication, calculate the entropy of both, so we can compare them, so run tests and change these entropies. And consider an environment with n possible states, and since at the start of the test the agents have complete uncertainty about this environment, we can calculate the uncertainty in an environment as the entropy of, which is minus log 2 of the number of states. So we will initialize the environment first, generate a set of agents, initialize the entropies for communication observation, run a test for 1,000 episodes, record the scores, which is an indicator of intelligence, and then we will change these HO and HC, the entropies, and repeat the experiments and record the results again and see what's going to happen. So we end up with something like that. So what is this? So each square here, or each cell, has a score for different communication entropies and observation entropies. So each cell here is one test, repeated 10,000 times. So, and for different communication settings, we have different results, of course. So, what are these? The intensity of the colors means that you have higher score. Okay, so if it's dark, it's high. It's not, all right? So, the first general picture here is that we can see some kind of pattern, all right? For stigmergy, for example, we see that the scores are, the maximum scores somewhere in here. I'm sorry, it's not very clear here. In the direct communication, it seems to be the same if you move that way or that way, so communication or observation. In imitation, it seems like you have a different pattern as well. So, how can we analyze these 50 shades of gray, or whatever you want to call them? So, we start by doing this. We have these results, right? The first thing we do is recalculate the scores for each, fixed communication entropies across different observation entropies, so, and vice versa for specific observation entropies and different communication entropies. So this is, these are the rows and these are the columns, all right? And after we do that, we calculate the average of these, and we have whisker plot, which, where the 25th and the 7th percentiles of the scores, and the scores extend to the maximum. And these, all right? So we will do this for each type of communication and try to analyze the results. The first thing that we notice here is that for stigmergy, or indirect communication, the scores increase when we increase the observation, which makes sense, right? So, and they increase kind of monotonically until they converge up to some point here. While we see some changes in the scores when we increase communication, the relationship between communication and the scores is rather more different here. So it seems to depend on observation. So we see that at different points we reach a peak, and then as we move away from this peak, the scores drop. And this was really strange the first time we got these results, so we didn't know what was happening. Why, if I increase the communication, I get a score at this, a very good score, and then if I increase it a little bit more, the score drops a little bit? Why does that happen? It means that when you increase the communication, it's not, you don't always increase the performance. And that's really important. So we wanted to analyze this dependency. And this happens for one type of communication and not another. So when we run a simulation here, we found that if I'm at this square, and I have strawberry here, and I can only see one square, and if I go and tell the whole environment that, whoa, this environment is full of strawberries, I mislead you because it might not be true. But if I can see most of the environment, and I tell you, look, this environment has strawberries and blueberries, I might be right. So what we noticed is, when we go over here, we find that increasing communication influences the results here, but not here or here. Why? Here, because I'm so myopic. I can't see, okay? And here, because the agents have enough information already about the environment, they don't really need this much communication. And in the other case, it's not the same. Let's look at direct communication. At first, we see that the effect of observation is kind of similar, so we increase it, we have better scores. In communication, it's clear here that we have a different explanation, and when we increase communication, we actually improve the scores. But if you increase communication for very low observations, you will not always have the optimal score. Okay? So when we look here, we see kind of similar plot, which says that, okay, increasing this or that will lead to the probably similar results. In imitation, and this is really nice, I find it really nice, because it seems that the intelligence of the system is mainly dependent on how much entropy is exchanged through communication, and not the other way around. Why is it better? Why do I get a better score when I imitate than when I can actually see the environment? Okay? That, of course, depends on the type of agent that you're communicating, and in this case, imitating, and in this case, it's an oracle, right? But, so what we find here is, if we change the observations at this stage, it has insignificant effect on the results. So while if we go to the same point and we change how much they can communicate, we see that the scores really shift. So the power of imitation here is made explicit. So we calculated the phi here, which is the success of communication over observation. So if it's close to 1, it means that communication has a higher influence, and if it's 0, it means it's the inverse. So what we found that is for sigma g, we have very low observation coefficient of success phi, which shows very high dependency of communication on observation. There is a huge dependency, and it's not the same in other communication modes. And we ended up with plotting this graph, which is entropy analysis. So it's shift in gradient in both directions, HO and HC. So this shows the points where communication is mostly effective above observation. And we see they reach the peak at different points. So why is it important? Because we find that in using different systems or agents or different communication techniques, these maximums change. So if you use different number of agents, the maximum score that you can get, or the optimality of the system, is found at different entropies. So if we can run these tests in different settings, we can actually predict where the system has the best performance. Or we can even reverse engineer the system somehow based on the number of robots we have, or the number of agents we have, or whatever. So of course we can measure learning rather than search, because we can we know how to calculate the complexity of the agents, or the movement pattern of the special agents. So we can also test across different pattern complexities or task complexities. And so we know that dull systems can be improved and we can measure how much we can improve them. We also know that if we increase the communication entropy, it does not necessarily imply that we will always get an increase in intelligence. And communication can be highly dependent on observation, and we can measure that. And also there is a restricted range of entropies where communication has highest influence. And we can run some tests also to find out where this range is. And what I want to say at the end is we can also find a lot of applications which use something similar, which is, for example, if you have pattern recognition problems or nest selection where there's only one best nest, and that's very important, because it's very hard to generalize these results when when you can get a reward from 2 different positive agents. This will change. So if there is only one nest, and your job is to find the best nest that will reward you, this is different than having 10 possible solutions, and all the solutions will give you the same reward. So we have to know that using different properties will lead to different results, or different tests. But we can still use this approach in order to find the properties of a smart multi-agent system somehow. And thank you. That's it.
Thanks, that was really fast.
Thank you.